We are today explaining how to work with RFEM and how to work with background layers to create the model and to create loads and combinations. We will then take a closer look to the reinforced concrete design and at the end create documents. The workflow in RFEM is in such way that you use RFEM, the main module, to create the slab and the concrete structure itself, including loads and combinations. Then you will use certain modules to do the design in concrete. The most important modules are RF concrete, that includes slab and beam design. There is also additional modules for punching design, namely RF punch, or for column design, namely RF concrete column. RF concrete NL is a more advanced module for nonlinear analysis, especially used for deflection of slabs and for deflection of beams in cracked situation. With RF concrete deflect, it is a more simple module that we can use also to analyze deflections of slabs. In the concrete design modules, we have following codes available: Eurocode 2, ACI 318, which is American code, SI 262, which is a code from Switzerland, GB 510, which is a Chinese code. Other codes are in preparation and will be also published on our website when they are available and finished. I would like to go now into the demonstration of the module itself and in the live demonstration in the software. For those of you who are new, you can ask short questions, and my colleague Robert Vogel will assist you with short answers. To ask questions, please use the small question text box where you can type in short questions. You can show and hide the control panel by clicking on the red arrow on top of your screen. Typically on the right hand side of your screen you see this control panel. In the live demo, we will now enter this structure that you see here on the screen, and I will leave the PowerPoint presentation and explain a little bit about the model itself. In many situations, you do not have a 3D model or a BIM model or a Tekla model or a Revit model, and you will have maybe only a sketch, but you might want to use this sketch to model your structure inside RFEM. Here you see a small slab ground plan made in AutoCAD. You see where the walls are. We have here a beam, we have a column, and you see some dimension. And I'm using this view as a background layer in RFEM to create the model very quickly. To do this, I open a new structure inside RFEM, and I'll have to enter a model name. It will be a 2D model, and it will be according to Eurocode EN 1990, especially the loads will be according to Eurocode EN 1990, and we'll use the general settings for the national annexes throughout this project. We'll create combinations automatically according to this code, and we'll create result combinations, which are linear superpositioned results of the individual load cases. Now I can import the background layer. Either you can use File, Import, and you see here DXF format, import as background layer, or you can also go to the Data Navigator and use the Guide objects, and Here you find background layers. Right click on it and create a new background layer. I'll import one DXF file I have prepared here as a background layer, and you can name it as you like, sketch from CAD. Also, you have the option to import from a specific layer that you can select here. You might have drawn already certain lines inside your CAD application that you might want to use for your boundary lines, for your surfaces, but in this case I import the entire lines that I find here. I click on OK, and you'll see the slab, the outlines of the slab already in the background. These are not real lines, I cannot touch them at the moment. Now the situation is so that my actual structural system will not be all the way to the end of the wall or to the outside of the wall, but maybe also already end in the center of the wall. And often it is so that as the structural boundary we use the center or the middle of the wall where the slab is placed on. So how to do this? I can now use a tool called Set Parallel Line. And with this Set Parallel Line tool, I can create a line that is offset of a line that I pick in this background layer. The offset I use here with the half of the wall thickness, which is in this case 18 centimeters. And now I can start clicking on the line, and you see in the center of this wall a line is created. And I can now just simply click on all the wall edges that I have in my template and go around the slab here to quickly kind of grab the geometry of the structure from this background layer. So I do not have to use any printed plans or manual drawings, calculate coordinates and so on. So the software is helping me here. Okay, one more here. And then I have a pretty good idea of my slab. So I have to make a few more adjustments. For example, here my drawing wasn't that good, so I can enter manually now a line. I can snap to the existing nodes and create a perpendicular connection here. I don't need this line anymore, and I can just drag and drop the neighboring node there. So with a little bit of manual work, I can fix up my model here. Here also I'd like to have a perpendicular connection. I just drag and drop it to the next line and fix my holes here. Okay, here maybe there is a node that I don't like to have. I can delete this node and merge the joined lines or members. So out of the two lines, one line is formed. Here again, I'll fix the little problems. This node I need, this node I need. Here it is all. There's a slight inaccuracy which is often happening when you work with DXF files. So we can fix this very rapidly with the tools that RFEM provide. Okay. Here we need a little bit, and one more situation here, and we're almost done. Again, here there is some inconsistency. Okay. One other thing is I have here certain rooms or offices that I would like to apply loads in separate load cases. So it's a good idea to create not just one slab out of, not just one surface out of this slab here, but create one surface for each wall. And that's why, for each room. And that's why I create here a few more lines so I can draw basically my rooms and the maybe I do it the other way. Hang on. So I have the correct boundary lines for the surfaces. Okay. Okay. Here we go. So once we are done, I can maybe delete this one node here. Once we are done, we can hide our background layer. And we can just either delete it, or we do not have to delete it. We can go to the display tree and just hide it. There's guide objects as well, and we just hide the background layers. Okay. Next, we'll have to enter the surfaces itself. So I select the boundary lines. I have here already in this model a couple of materials. I use them, concrete C37. Of course, I can always pick something from the library that comes with the software. The thickness should be 300 millimeters and it's a standard surface type. I'll click on the boundary lines and quickly enter my surfaces one by one. And each surface represents one room that I might want to use later. Okay. Okay. Here we go. And we are done with the surfaces. Next, we'll enter quickly the linear supports from the walls. Okay. I can either enter a rigid linear or hinged linear support, or as a specialty in RFEM, I can use a so-called elastic support via wall. This tool automatically provides the stiffness of the wall, and for this I have to enter the dimensions of the wall. So the thickness is 360 millimeters, the height is 3 meters. The material of the wall I can pick here, for example, from masonry. RFEM has in its library also the option to create certain masonry wall types made from brick and composed with mortar and all the parameters that Eurocode uses. So it's quite well, a lot of parameters you have to use in Eurocode to get actually the correct material parameters for the masonry used to be in the wall. So from these parameters I can create then the modulus of elasticity, the shear modulus, and so on that I need for an analysis. I'll use a linear elastic material law for this, so I'm not using a nonlinear masonry material model. Okay, and I also can address the support condition of the wall on top and bottom, and I will choose the hinged support condition. Okay, and I see as a result the stiffness for the vertical support of this created from this wall with the specified dimensions. Okay, next I'll just click on the lines that are supposed to be supported. This one maybe not, I can erase it later. Okay. Okay. and one more here. Okay. Accidentally I entered the support as well here. I'll delete it. Next will be point supports, nodal supports. I have a column in this area here, and here I have an equivalent way to do it. There's also the option to select column, and here I have to have the dimension of the columns and the height of the columns and the material. This time I stick with concrete. It should be also hinged, and I can model it as an elastic surface foundation. That means basically the software uses the 300 by 300 rectangle for an elastic support underneath the slab, and this is a better model as if there would be just one node connected to the surface model. So we have a more a small area that is elastically supported, and that will help to avoid singularities later on. Also at the same time, it will not show any results inside the column, which is more or less the column material, and it doesn't make sense to make a design there. And I get design actually at the edge of the column. Okay, I forgot to have a support here, so I quickly actually I can just drag and drop it, Control and left mouse key pressed, and then drop it to the next neighboring line. So now everything seems to be all right. And we are about ready with the model. Finally, I need to here enter the beam that helps to support that wide span here of this surface. For this I select the lines. I'll enable or make a member available, and for this I need a cross section. I enter here rectangle 400 times 600 and made from concrete as well. And as a specialty here, I'll create a so-called rib. A rib will place the cross section, the rectangle, below the surface, and I can control it here with these radio buttons. Now the position will be on the plus C side of the surface, and at the end I will get internal forces from this beam composed of the part of the surface and the beam itself, the rectangle cross section below. And I have to specify the effective width of the part of the surface, and I can do this here with the effective width on both sides. So the software will then integrate the internal forces in the slab into 1D member internal forces together with the beam, the eccentric beam that is located below the slab. We will see the forces then later as beam forces. And we will also design this T shape in the member design of our concrete members. I can also take control of the rigidity stiffness of this part, of this beam part below the surface, because in correct situation the torsional stiffness of the beams are reduced pretty much. Often in standard practice it is so that you reduce the stiffness of this beam when you analyze the internal forces. I'll leave it here for 100%, but I just wanted to let you know that you have this option. By clicking on OK, we'll see the eccentric beam here below the surface. Okay, this is the model, and now we can maybe already start with my documentation for this slab. First of all, I'd like to show the numbering of the lines and of the surfaces, because those will then also show up in the tabular output of the printout report. And I'll print this picture to the printout report. This should be maybe 50% of a page. And I'll click on OK. And the printout report template I'm going to use will be from one that I prepared before, RF Concrete 2D. We see a short preview of the printout report with all the tabular input and the picture that we just printed. So everything that I entered now is here already in a tabular format, and it's documented for checking later on. You can maybe zoom it to 2 pages, which gives a very compact view of the printout report. Okay, once it's created, I close it again and I save it. Next, we'll have to deal with the loads and load combinations. I can do this either here, create new load case, or I can do this in the tables. And in the tables, it's maybe more simple because I can just work like in the spreadsheet type, and it's quite quick. First load case is self-weight. Second load case is some live load, and it has action category imposed office area. And it will always remember the last input, so what I have to do now is just enter quickly the other 8 load. We have 7 surfaces, 8 load cases in total. Okay, after this, I have the next table, which will sum up all the load cases in so-called actions, and I can select which design situations I would like to work with. For this example, I will use the ultimate limit design situation and the serviceability design situation, which is the quasi-permanent combination in Eurocode. After that, I get action combinations. Load combinations will stay empty because we work with result combinations, which are combinations that overlap linearly analyzed results. And at the end, we will mostly work with the result combination 5 and 6, which will include the envelope of all the design situations and serviceability situations. Note that we will use in the design situation additional partial safety factors, 1.35 and 1.5 for the office area. Okay, this is the combinations and the plain load cases. Next will be the loads itself. We'll create a new surface load for the self-weight load case, 2.5 kilonewton per square meter, going to all the surfaces. Next will be the live load, 3.5 kilonewton meter on each surface individually per load case. I can just change the load case while I'm still in the entering mode of the load itself. So this way I'm rather quickly with entering those load cases. Last but not least, I will take a look at the mesh generation parameters before I run the calculation. In the mesh settings, I set a target length for the finite elements of 500 millimeters. And if I work in a 2D plate XY structure, I have an additional option that allows me to make a finer mesh along the edge of each surface. And you can control it by this parameter here. So this is a good idea because where I have the linear supports, and mostly they are at the edges, I have large gradients of stresses, and especially for shear forces, it will somewhat condense those extreme values closer to the edge inside, if you want so, inside of the wall. And they will not be disturbing the design later on in RF concrete surfaces so much. Okay, and I do one more mesh refinement that will be done in the area where I have the point support. Here I can just select the node, right mouse click, finite element mesh refinement. I create a new one. I'll use a rectangular type, and I'll take over the default parameters which fit very well to the dimensions of the column with 0.5 meter at the moment. Inside there is a finer mesh, and on the outside there will be actually the target length of the global FE mesh that I just said before. So there's a good transition from the finer mesh to the global target lengths of the finite element mesh. Okay, with this I can start the analysis. So I can calculate all the results. Mesh is created automatically in the background, and I'll see for each load case now first the deflections. I can also view the internal forces, maybe in the top view. I can now also control, like if I want to see the finite element mesh or not, if I want to see my supports or not. I can maybe hide the support lines because I don't want to see them now. I'd like to see the results. Okay, this picture now is good for documentation. I need my internal forces to put into the document. So how to do this? I have here the panel that indicates the magnitude of the forces, and how to do that. I can print and use the mass print option. In the mass print option, I scale it to 50%. In the mass print option, I have the option to control the results of maybe selected load cases. Maybe I only want to see my final results, the ultimate limit and the quasi-permanent results in the envelope. And I click OK, and I want to see MX, MY, MXY, the shear forces, everything I want to have in this in the protocol. On OK, I'll then check show printout report on OK. I disable it because I don't want to always open the printout report. I just will drop it in my final printout report. And I click OK, and RFEM then dumps it into the final printout report. Also of interest is not only the surface support, surface internal forces, but also the support reactions. I enable them here, and you see that you can't see them because they are drawn below in direction C. How to fix this problem? RFEM has a specialty that for 2D surfaces, it can display the support reactions. They can draw them in XY plane. So I can kind of swap them over, and then I see the support reactions here in a much better view. Often engineers do not work with the real lines of the support forces because when there is a masonry wall, the force transfer is not one-to-one from the support of the slab down to the next maybe wall below. There's some kind of distribution that is depending on the stiffness of the material that is used for the walls. So in many cases, it's also suitable to work with smoothed, mean, constant forces. So what we do is we integrate all the support forces along the line and average them to a mean value. So this is a good way that how you can maybe use those this information also for a load on the next story that you have maybe below. So this type of picture I would like to print also in the printout report. So I use again the mass print option. I'll click on detail setting, results, and this time I'm enabling the support reactions and local PC reactions, line supports, and also the nodal supports. Okay, I don't want to do it for all the results. I only want to do it for the individual load cases because when I keep on calculating with those forces, it's a good control, first of all, and second of all, I might have to apply different safety factors, so the result combinations really don't help me very much if I print them. Okay, all load cases, all images of all load cases are printed in this way. Okay, then next picture is maybe the member internal forces that I have to take a look at. If I look at my internal forces here, I can see here there are beam forces, bending moment, shear forces, torsional moments, and so on that come from the twist introduced by the slab. I can print also this result, but there is another good way how to document it. It's in the so-called result diagram. And I can use this result diagram and print all my forces, maybe also including the deformation, into the printout report. And this time again I use the envelope. Maybe we stick with the bending moment and the shear force. Maybe we add the torsion. Okay, we print this to the printout report. I will use an entire page for this time. Okay. Good. Now we have already done all the internal forces, support reaction, bending moments, beam results. Next, we'll go to the concrete design. Here we'll first use the module RF concrete surfaces, and the RF concrete surfaces module will design the surfaces as it says. We'll use for the ultimate limit design the result combination 5, which includes all the envelope, all the results of all the individual combinations. We use Eurocode with the general settings of the Eurocodes, the standard setting of the Eurocodes. For serviceability limit state design, we use the quasi-permanent combination. We can check the materials, which are just taken over from RFEM. We'll see in the surface pane, we'll see a list of all the surfaces, and I have different options here to check. First, we need to check the stresses. This is part of the serviceability check. The stresses for the concrete that takes over the compression. Regarding the code, there are certain settings that limit the compressive stress, and you can just choose them. Everything is set up by default, so in general you wouldn't have to change anything. Also, stresses have to be limited. For example, typically to 80% of the yield stress of the material. If you want to, you can set those settings individually for each surface. And the next thing is the crack width control, and here I have to define, first of all, what is the limiting crack width. It should be according to the exposure class, and in this case I have XC1, which will be resulting in 0.4 as a crack width, as allowable crack width. then the Eurocode knows 3 different options how to control crack width. One is by limiting the diameters, another one is by limiting the maximum spacing of the bars, and the third one is the direct analysis of the crack width, which is the most sophisticated, I would say, and therefore I'm just using this one option instead of doing the same check 3 times. If it is important, you can also analyze a minimum reinforcement for effects due to an internal restraint. In this case, we don't have this. This can have a significant amount of free bars as a consequence. But this slab can float free on the walls, so there is no restraint basically, and we can ignore it. Okay, this was some settings regarding the serviceability check. Regarding the reinforcement, I'll first have to have an idea how much of reinforcement I need. And then I can decide if I put there a basic reinforcement that will be everywhere on the slab, or if I have like 2 layers of reinforcement. One is a basic reinforcement and another one is an additional reinforcement. The reinforcement layout is done in the second tab here, where I first have to define the concrete cover. Here I can just pick it from the exposure class of the code, and it can be differently on top and on bottom of the slab, because one can be exposed to an outside, one can be exposed to an inside. Then you have different concrete covers that you need to check. From these parameters, RFEM or RF Concrete calculates the required cover. For the longitudinal reinforcement, I can already set a basic reinforcement, which I will do later, but first of all I want to have a first run of the analysis and see what situations do I have. And in the next tab I can check whether I need minimum reinforcement. This is the ductility reinforcement basically, and the minimum longitudinal and the minimum shear reinforcement. This is required also by the code. There are several safety factors that we can address due to the type of the loading, whether it is persistent and transient, accidental, or serviceability. Those are actually national annex parameters and will be set according to the national annexes that you choose. Okay, those are the most important topics I would like to point out. The national annex parameters can be shown down here. You can change them and also set them up differently if there are changes in the national annex or whatever. Also in the details you have an option to, maybe one point I need to point out, which internal forces you use for design. Remember, we have a beam and that uses already a part of the, or integrates part of the internal forces from the slab, and I'll get a design then in the next step for this T section. So this part of the slab that's already part of the design in the member, in the beam, I do not have to apply for this surface design. At least in the direction of the longitudinal direction of the beam. That's why I check this checkbox here, and I will not use it for the surface design. Otherwise I will get reinforcement from the slab design or surface design and reinforcement from the beam design, and that would be double, and I don't want to have that. Okay. Now I'm ready to run the analysis and get a first idea about my reinforcement. We have a required reinforcement of about 20 square centimeter per meter on the top, in the second direction, on the top, bottom direction, two directions, top, first direction, second direction. We also get a overview about the serviceability design. We'll see here there are some problems as well with cracking and also with concrete compression. Let's take a look where we have those problems, and I go to the graphic, and we get first the display of the required reinforcement on the top. On the top in the other direction. Note here the direction is indicated by these little red marks. Then we have the bottom reinforcement in one direction, bottom reinforcement in the other direction. We see here now direction longitudinal to the beam takes out the design pretty much of this reinforcement where we have defined the beam. So RFEM knows that there was 1.60 meters left and right of this beam, and this section will be part of the beam design. Okay, let's take a look of the content that we need of rebars. If we see like the blue and the greenish areas, we talk about 4.8, 4.08 square centimeters per meter. So if I would cover this with a basic reinforcement, I would have only a few spots where I would have to have additional reinforcement. For example, here. And if I look at the other direction, it would be, if I do here also 4, then it's greenish. All the green parts will be taken care of. So if I look at the top reinforcement, let's say 4 would be pretty much of the dark blue would be covered, only a few spots left. So I'm trying now to add a additional reinforcement or the basic reinforcement on the surface, on all the surfaces. Go to the reinforcement layout and longitudinal reinforcement, I'm sorry, and here I can enter an existing provided reinforcement. Here either I pick a diameter and a distance, and I'll get the content of reinforcement shown below. For example, I can use a 10 millimeter bar every 200 millimeters. It will be about almost 4 square centimeters per meter of reinforcement. Or I can use wire fabric that I can buy, maybe cheaper, or it's easier to mount, and I can use some quadratic wire mesh for top and bottom. And this I'll use already for my design. It will play an important role for the serviceability check as well, because the diameter plays a role here, and I have already an existing reinforcement there. Okay, I run the analysis again, and now I have different options to display my results. First of all, I have here a little bit less, well, required is the same, but I have here additional required and required, so there's the difference here. This is the basis reinforcement. I can look at these results also by surface or by point and so on. If I want to, I also can look into the design details. So for every mesh point, I get an enormous amount of detailed results that I can use to check my analysis if it is correct. So if there is one question, one doubt about the result, I can go there and I get all the results, I get all the details. So for every point on the, for every mesh point on the structure, I can, or for every grid point actually, I can get those internal details. And we have a very powerful way to really see what the software is doing internally. Okay, and the same is also here for serviceability design, and I see here, okay, with the crack width we are fine. there's only a small problem left with the compressive strengths, and if I click on here, I see it's here where I have a punching problem actually at the end, and I will have to do something anyway with it, but maybe I can just neglect this part here for now. When I go to the graphics, I have now additional options. I can show first of all the required reinforcement, what we've seen before, but now I can also say I want to see the required additional reinforcement. So it shows me the difference of what I have provided by a basic reinforcement and what I have to add additionally. So here, this is for the top, so there's pretty much nothing, just at this point we have to think about doing something, and here we'll do a punching check later on. And on the bottom, here I have maybe in this area I need to have extra reinforcement. Here is a small area, but there's only about 1.292. Maybe if I add a little bit more on the basic reinforcement, after all, I have not to do anything here anymore. And the same thing is in the other direction. When I take a look at the serviceability, I can check my concrete compressive strength, stress, and I get ratio. If it's greater than 1 and it's exceeded, if it's smaller than 1, it's fine. So we have the yellow parts are pretty much okay. The steel stresses are okay overall, and I have my crack width. So I have only cracking that appears here, a little bit here, it's not surprising, over the wall, and of course here, but this part again we have to take a closer look later. Also I can check the crack width on top and on bottom, maybe on bottom in direction 1 and bottom in direction 2, and also the resulting, the resulting of both directions can be shown. Okay, I'd like to also show some values on the surfaces for printing, because we also want to print, of course, the results. So maybe it's better to reduce the values for that I get only one value of per surface of the max and the min value. So each time I change the result, those values will be then also adjusted. I go to the reinforcement, maybe the required reinforcement, you get a nice view, also including some values, which reinforcement you have there. Okay, those pictures I'd like to print again. So we'll print this picture. We use the mass print option. We'll use again 50% of page size. And also for the concrete module, I have the mass print option that I show all the results, all the rebars or rebar content on top and bottom in all directions for all cases, and also the same thing for the required additional reinforcement. So all in all, it should be something like 8 graphs. I click OK, and I drop it again in my printout report. So far about the design of the slabs. Next will be the design of the members of this beam here. We enter the concrete member module, and we use for the ultimate limit, we also use Eurocode, and we use for the ultimate limit design the result combination 5, and for the serviceability limit design result combination 6. This time I also activate creep and shrinkage that we can use here for this beam. And I'd like to point out that we can also do for beams and also for the column module, we can do fire resistant design. So if that is needed, it's also included in are concrete members and for the columns. So next we'll go through the materials, check the materials, check the cross sections. Next point will be ribs. As I said, we use part of the surfaces for the member internal forces, and we entered it inside RFEM. So what we're actually doing is we're designing a T section, and the internal forces come from the surface and the beam below it, and they are integrated to one member. So the effective width is given here. You have the option to change the effective width in the design module if you want to. So when you have a negative moment or a positive moment, you can design a smaller cross section where there are cracks, for example, and a bigger cross section where the slab is in compression. So there are various options that you can use, and in the Eurocode there are some requirements regarding this. I'll stick with the simplified method and just keep everything constant at the moment. Also, I can reduce the shear forces that are near to supports, and I'll have to indicate where the supports are, and they are here at those points, and I have to indicate whether it is an end support or an intermediate support, and I have to enter the width of the support. So this will optimize my results in there. Next, I'll go to the reinforcement. We can now enter design which diameters are possible. So we choose 14, 16, 20 millimeters of longitudinal rebars. Same thing for the links. We can define which diameters we want to use there. We can use certain spacing of links. There are certain options that you can use. Reinforcement layout, it's similar to the reinforcement layout that we had in the surface model, where we, for example, have to find the cover of the concrete. I use again exposure class XC1. Yes, minimum reinforcement, ductility reinforcement is taken care of, and I need to have the concrete cover setting as well. Okay, with this I'll start my analysis and run the design of the beam. We see here first an overview again about the required reinforcement and the provided reinforcement. So you get a reinforcement suggestion that you can use. We can also use a 3D rendered view that we can show. We can print this to the printout report as well. Here I use again 50% of a page. Same thing for the shear reinforcement. You get here a sketch of the shear reinforcement that will be also part of the printout report. For the serviceability check, we see here that we have actually crack width of 0.2 for the maximum. The deflection is here, and everything seems to be quite okay. We can take a look at the graphics. I'll show here the graphic view of the beam, and we see here the top and the bottom reinforcement. As well, we can show the provided top and bottom reinforcement. So we see the software provided more as required, so we're on the safe side. If you want to, you can subdivide those members and make it more individual along the beam. I can print also this picture to the printout report. Printout report 50%, okay, as screen view, and we'll print it. Also, I can show my serviceability checks. We can see the compressive stress for the concrete, for the steel, the tension stress, and I can show also my, maybe I take 2 pictures, print this, okay, and then I print another one with the crack, location of the cracks and the deflection, and print this as well. Okay, this is the design of the concrete members. After all, we can now maybe take a look at our printout report, and I'll just make a quick save in between, and then see how the printout report looks like. I have the printout report here in the data navigator, and with double clicking on it I can open it. And we should see some more data as before. Okay, it takes some time to build. Okay, so I'd like to view maybe 2 pages at once, and I can see here my support reactions that I printed before. I can see here also my internal forces that I printed for all the design situations. I see my internal forces for the beam, all the tables that I have here regarding the concrete design, and I don't have results here of the concrete slabs because I didn't analyze those results, but the beam is here, and we see here the pictures that I printed individually just before I opened the printout report. Altogether we have 31 pages. If I want to see the results of the surface design, I have to close it again, and I have to analyze the results of concrete surface as well, and then I should also see those results in the printout report. Okay, let's open it one more time. And then I think we are pretty much also at the end of this demonstration. So now let's see if we can see all the other results of the concrete design. RF concrete, here we go. Takes some time. It loads the results while we are navigating, and here we see also the reinforcement and everything. It seems to be clear here again. Okay. I have picked at some of the questions that have come in, and one question was about that was more or less several times a question, is about real deflection of the slab in the cracked situation. Now everything was pretty much linear deflection, but if I want to have the real deflection of the slab in the cracked situation, I can do this with the module RF concrete surface RF concrete deflect, or which is in the which can be found in the surface module. Therefore, I open the surface module, and but we have to do a little bit work beforehand. The serviceability limit state, I can go to the analytical method here, and I can see here deflection with RF concrete deflect, and here I can also enable shrinkage and tension stiffening and creeping and so on. This is a more or less nonlinear analysis, and I cannot use a linear combination of results in an envelope. So when I want to do it, I cannot do it for the result combination 6. I have to provide an individual combination. Now, when we look at the internal forces, or let's look at the quasi-permanent results. When I look at this, look at the deflections. You can see here that the deflections are biggest in the area where is the wider span. That's kind of clear. Here it's not so bad, but here is the problem. So I have to find a load situation where this slab is mostly loaded, yeah? And I have to make a load combination and not an envelope, not a result combination. So what I do now is I use maybe load case self-weight, which the load is all over, plus where the load sits on this slab. So load case 1 and 2. And I can anytime, you do not have to work with the fixed load combinations that are created by RFEM. I can anytime create my own load combination with my own safety factors. And I do this now. That was the wrong switch. And I create load case 1 plus factor 0.3, which is the typical safety factor for the permanent combination of the live load. Okay, click OK. Did I do wrong here? 0.3, and then here I need to have the delimiter. Okay, and then I have here my load combination, which I will use for the deflection design. Here now I have an individual situation, all the loads are there and displayed like this. I can run the analysis of this load combination and get a set of results. Note, the deflection here is 3.6 millimeters. When I do this now in RF concrete, in the correct situation, I'll get the following result. Let me open the module one more time. I'll do following. I'll uncheck this again and do not use the deflection module here. Here we analyze the regular results. We can do this quickly. And then I'll copy the case. I'll copy the same thing and I call it deflection. So I work with the same settings when I analyze the deflections, and here I said then I would like to do the deflection analysis. Okay, but not with the quasi-permanent combination, but with the combination that I just created for deflection. Okay, I run the analysis, and now it's a nonlinear case. And at the result, I get a nonlinear deflection. And we can look it up in the Serviceability Design. And here we see we have a UC local total of 16 millimeters is the existing value. Limiting value is not quite right. I forgot to set this. When I do the deflection analysis, I'll get different tables here with the deformation analysis, and I can set here the limiting value. So I can analyze the limiting value as a when I divide the maximum length divided by 250, for example, and I can pick this distance here from here to here, for example. So we talk about 7.8 meters, and the limiting value will be 7.8 8 meters divided by 250. And when I run the analysis again with this limiting value, we should be quite okay. And we see here we have required is 16 and, oh, hang on, total. We have here limit is 31 and we have on the 16, so the utilization ratio is 0.6. And the concrete stress problem is again here at the column. Okay, which reminds me that I also have to show the punching that I forgot. Please note that we have the deflection. We can also show this now here in the graphic view. Results, serviceability, deformations. We have here 16. And if I show the same thing, maybe I can view a window, different window, new window, window parallel. And here is the nonlinear, and here will be the linear, which is only 3.6. Is that correct? Yes. So we have about, or almost now, 4, 3, 5 to about 4 times more of the deflection, between 4 and 5 times more of the linear deflections we have in the nonlinear situation. Okay, this was this question, and then let's take a look at the punching check. We have here this situation where we have a lot of force that is concentrated on this column here. With the module RF punch, we can check this, and this will not take us very long. We'll open it. I'll use the ultimate limit design situation. I use Eurocode again. Materials, we've seen several times now. A specialty is that I can take into account openings around the point support that will reduce the shear capacity or the capacity against punching. I can enter the location and the type of the openings here. We have longitudinal reinforcement that can be defined by the cover and by the direction, and which is now, as always, 0 and 90 degrees. And we have here the individual node for punching. It already knows that it is it already knows the node where there's just one support, node number 6, which is also set up here. We know the surfaces that are connected to this node, and I can put here the dimensions of the column. Okay, I can enter here all the code parameters. I assume the position is somewhat in the middle of the slab. The shear reinforcement should be designed, if so, vertical. I want to get the reinforcement should be laid out. So it will now create a reinforcement first in longitudinal directions, and if I can provide enough reinforcement that punching is not a problem, it will not introduce any shear reinforcement. Okay, and with this I run the analysis, and I get here a design criterion of 1. And if I look at the details, I have effective, what is it? Where is my reinforcement content? We can take a look graphically as well. So the applied force is 659 kilonewton with the maximum shear stress, basically. There are moment in center of perimeter in x direction, and all those minimum moments that have to be taken into account are set there. We have here's the applied shear force, 925 kilonewtons. The governing punching load is the same, and then we should get some required reinforcement at the end, and we actually the design is the resistance for shear and the maximum force which is there, and the criterion ends up then as 1. If I look into the graphics, I can show my required reinforcement on top, which is 22.4. I can also show again the value. Maybe this time I only want to have the extreme value. Top, the other direction, and I get my values as well here. So this is the punching shear check, which is done in the module RF punch. Okay. This was the live demonstration. I'm sorry for the slight problems that we have, but this is live demonstration, and things like this I guess can happen, and I'm apologizing for it. I hope it still was a good webinar for you and you've learned something. If you need more information, you're welcome to visit our website. You can follow us also in our social media channels or in our Dlubal blog that's also available on the website. Also, do not hesitate to download a trial version. You can test out the concrete design yourself with the trial version for 30 days. I'd like to also inform you that there is another webinar at the end of October. This time then will be about advanced steel design using RFEM, and there's more webinars planned also later this year. This webinar that we just had will be recorded and will be also online during the next days, and you can take a look at them in detail again. And yeah, thanks for your time today, and I hope you'll be part of a webinar again in the near future. Bye bye.